Previously, we have looked at several examples to calculate Gibbs free energy change for a reaction under standard condition, and from the free energy change we can get the standard cell potential, or in a reverse way we get the standard cell potential from standard electrode potential series, and then calculate the standard reaction Gibbs free energy change. So now let's look at one example at non-standard condition. Non-standard condition. So for a reaction, delta Rg, reaction Gibbs free energy change under non-standard condition, under general condition, would be given by delta Rg0, the reaction free energy change under standard condition, plus a term which is RT ln K, gas constant, absolute temperature times the natural log of K, which is the reaction quotient or reaction constant. Okay, so this equation we can calculate the reaction free energy change for non-standard condition. And of course, reaction free energy change would be equal to minus NFE. Free energy change would be equal to the electrical work done by the system to the external or environment. As a result, the cell potential under non-standard condition would be delta Rg, reaction free energy change, divided by NF. And if we write it, reaction free energy change is two terms, so we would have the cell potential would be delta Rg0 divided by NF with a minus sign, minus the RT over NF times natural log of reaction quotient. So this equation enables us to calculate the cell potential for an electrochemical reaction if it is under non-standard condition, if the concentration or the pressure are not standard. Okay, and if we from earlier, the first term minus delta Rg0 over NF, that will be just the so-called standard cell potential. So the reaction cell potential would be standard cell potential and a term to correct for the concentration and pressure effect, which is RTNF ln Q. Don't forget the minus sign here. Okay? So with this, let's look at an example. We want to calculate the Gibbs free energy change and cell potential for the following reaction, again at 25 degrees C or 298.15 Kelvin, and the cell contains two metals, aluminum on one side, copper on the other side. Each of these metals are inserted into a solution that contains, respectively, aluminum 3 plus ion and copper 2 plus ion. The double vertical line between the two electrolyte solutions indicates something like an ionic permeable membrane that separates the cation, or something like a salt bridge that prevents mixing of these two cations. Okay, so we want to calculate the free energy change and cell potential for the following reaction at 25 degrees C. So this is the overall cell, and let's think of from electrochemical reaction point of view. The anodic or oxidation half cell would obviously be for the aluminum, the more active metal aluminum, to give out 3 electrons and become aluminum 3 plus, an ion in aqueous solution, and let's assume the solution concentration is 0.15 mole per liter. And E0 means the standard electrode potential, or the standard potential for this redox pair, aluminum 3 plus aluminum metal, for this redox pair, or for this half cell reaction would be minus 1.66 volt. Again, this is against SHE, or standard hydrogen electrode. Similarly, the cathodic or the reduction half cell reaction would be for the copper 2 plus, the copper ion, to combine with electron, copper 2 plus, so combine with 2 electrons to form elemental copper atom, and it got deposited onto the copper electrode. For this cathodic half cell reaction, the standard electrode potential for this redox pair, copper 2 plus copper, would be 0.337 volt, 0.337 volt. So now we have the standard electrode potential for each of these redox pairs, one for aluminum 3 plus / aluminum, the other for the copper 2 plus / copper. So with this information, the overall of full cell reaction, how do you get the overall full cell reaction? Remember, to get that, we have to aim at eliminate the electrons. Eliminate the electrons. So the anodic reaction involves 3 electrons, while the cathodic half cell reaction involves 2 electrons. To add them up, left plus left, right plus right, to eliminate electron, we have to multiply by coefficient. For the anodic, we have to multiply coefficient of 2, while for cathodic, we have to multiply a coefficient of 3. So for 2 times, say, 3 electron, we get 6 electron. This 2 electron times 3, we get 6 electrons. So the electron will be cancelled out, which means in order to add them up, we need to multiply a factor of 2 for the anodic half cell reaction, both sides, and a factor of 3 for both sides of the cathodic half cell reaction. And if you do that, this would be the so-called overall or full cell reaction. 2 aluminum atom combined with 3 copper 2 plus ion to form 2 aluminum 3 plus ion and 3 copper. Okay, so for mass balance, 2 aluminum on the left, 2 aluminum on the right, 3 copper on the left, 3 copper on the right. So the mass is balanced. What about charge? 3 times 2 plus, totally 6 plus on the left, 2 times 3 plus, totally 6 plus on the right. So we would have this full cell or overall electrochemical reaction that is balanced in terms of both mass and charge. And of course, keep in mind that the concentration for these electrolyte solutions that contains copper ion or aluminum ion are not at standard concentration. Okay, pretty low for both of them. With this information, we can calculate E0, which is the cell potential. Based on what you learned before, it will be the standard electrode potential for the cathodic half cell reaction minus that for the anodic half cell reaction. And the cathodic half cell reaction, as we said, would be 0.337 volt, as shown here, while the anodic half cell reaction would be minus 1.66 volt. And don't forget, that's another negative sign outside of the bracket. And then if you plug the number in, you would get the standard cell potential for this overall or full cell reaction would be 1.997 volt. 1.997 volt. Okay, this is what we get. We get the standard cell potential. Then keep in mind the electrolyte solution are not at standard concentration. And what about the number of electron transferred per progression of this chemical reaction? I said N equals to 6. How do you know? Well, when you add the anodic and the cathodic, you have to multiply the anodic by a factor of 2. So 3 electron times 2, that will be 6 electron. Well, for the cathodic part, the 2 electron you have to multiply by 3. It also gives you 6 electrons. So you would cancel out. That means per mole of progression, totally 6 mole of electron will be transferred for such an electrochemical reaction. And because the electrolyte solution are not under standard concentration, the reaction quotient Q, which we also sometimes write as this K, would be for the products copper, aluminum 3+ ion. Okay, the activity for aluminum 3+ ion, which would be equal to concentration divided by standard concentration. The activity for elemental copper would be 1, which is neglected here from the numerator. For the denominator, it will be for the reactant, which is copper 2+, modulated by the standard concentration, and it has to be to the power of 3 because of the non-stoichiometric coefficient of 3 here. For the aluminum concentration, it needs a stoichiometric coefficient of 2 because of 2 aluminum in this overall reaction. So if we plug the number in, and the C0 and C0 are got cancelled, we would have the reaction quotient would be aluminum 0.15 to the power of 2 divided by 0.025, but for copper, but to the power of 3. And the end result would be 1440. The end result will be 1440. This would give us the reaction quotient of K. So then, from Nernst equation, the actual cell potential would be standard cell potential minus, if it at 25 degrees C and 1 atmosphere, it would be 0.0592 volt divided by N, the number of electrons transferred per progression, times the log with a base of 10 of the reaction quotient. Okay, and if you plug the number in, E0 would be 1.997 volt, 0.0592 volt, we write it here, and N would be 6, and we keep the log for 1440, and if you calculate, it comes out to be 1.97 volt, which means for the overall reaction from aluminum metal and the copper ion to form aluminum ion and copper, it has a very large driving force or electromotive force, and the cell potential would be 1.97 volt, assuming no internal leakage. Okay? Then, on the other hand, if we use the standard Gibbs formation energy data, the standard Gibbs formation energy data from our CRC handbook, we would be able to calculate delta RG0 reaction, alpha reaction, Gibbs free energy change under 0 for standard state would be the summation for products minus summation for reactant. And for product, aluminum, okay, but don't forget that's a stoichiometric coefficient of 2, so the 2 would be in front of that GF, Fg for aluminum 3+, and the 3 of formation energy for elemental copper, but for elemental copper it's just 0, so this term would be neglected. And then for total reactant aluminum, you write it down here, delta Fg0 for aluminum, and don't forget for aluminum you have the coefficient 2. But anyway, the delta Fg0 for aluminum would be 0 because the reference state would be the pure aluminum metal. And plus 3 times because of the stoichiometric coefficient times the Gibbs formation energy for copper 2 plus in aqueous solution for this reactant. And then if we find the data from CRC handbook using a link, we would know the aluminum 3 plus ion has Gibbs formation energy of minus 48.5 unit of kilojoule per mole, plus 3 times 0 because the formation energy for elemental copper would be 0, minus the formation energy for aluminum is also 0, 2 times 0, the coefficient, plus 3 times the Gibbs formation energy for copper 2 plus ion. And if you check the literature, check this HRC handbook, it will be 65.5 kilojoule per mole. And then after you put the number in, the reaction free energy change for this reaction from aluminum metal with copper ion to form aluminum ion and copper, it will be minus 1166.5 kilojoule per mole. Okay, again keep in mind this is for 1 mole of reaction progression. It doesn't mean 1 mole of aluminum 3 plus got consumed or 1 mole of copper 2 plus consumed or aluminum 3 plus ion that got produced. It just means 1 mole of progression, but it actually involves 2 mole of aluminum 3 plus produced or 3 mole of copper 2 plus consumed. Okay, so once we have the delta Fg0, the standard Gibbs free energy change for the reaction under standard state, then we'll be able to calculate delta Rg, which is delta Rg0, the standard reaction Gibbs free energy change plus the RT ln Q or ln K term. And you plug the number in, we would have T, of course, 25 degrees C, 298 Kelvin. R is 8.314 joule per mole per Kelvin, and the natural log of 1440. We would come up to get a number for delta Rg, reaction free energy change of minus 1148 kilojoule per mole, a very negative number, which means from aluminum metal and copper ion to form aluminum ion and copper is highly energetically favorable process. Okay, anyway, with this delta Rg, the reaction free energy change value, we can calculate the cell potential. But remember, it doesn't have 0 because the concentrations for the calculate is not under standard concentration. So E would just be delta Rg over NF. Delta Rg is what we just calculated. It's minus 1148 kilojoule per mole, and N, similar to before, would be 6, and F is Faraday constant, 96,485 coulomb per mole. You plug the number in, the calculated cell potential would be 1.98 volt. Okay, so you see we can get the same, almost the same cell potential either directly using standard electrode potential series and correct with Nernst potential for the concentration effect, or we can first calculate standard Gibbs free energy change for the reaction and correct using the reaction quotient time for Gibbs free energy term, and then calculate standard cell potential, and the result should be very, very close. Okay?